We've seen rational functions and polynomial functions. Let's move on to exponential functions. This is a fundamental topic. You got to understand it. It's one of my favorites. So an exponential function is a function of the form f of x is equal to a to the x for some positive value of a. So, for example, I could have 2 to the x, 3 to the x power, 10 to the x power. So any positive number to the x power is an exponential function. You could even have fractional powers, so 1/2 to the x is also an exponential function. You just have to have a positive number in there. Let's graph an exponential function to see its shape. So here is the graph. Let's do 2 to the x. So if I graph 2 to the x, then if I plug in 1, I should get out 2 to the first power, which is 2. If I plug in x equals 2, I should get 2 squared, which is 4. If I plug in x equals 3, I should get 8. But 8's way high. I'm not going to actually plot it on this picture. The numbers in the graph of an exponential function increase exceedingly rapidly. So if I plug in x equals 3, I get 8. If I plug in x equals 4, I get 16. My picture is going to get really high really rapidly. I could also plug in 0 and negative values. So if I plug in x equals 0, I get 2 to the 0 power. Anything to the 0 power is equal to 1. If I plug in negative 1, I get 2 to the negative first power. That's the same thing as 1/2. So I get this value here, and then if I plug in negative 2, I get half of that. If I plug in negative 3, I get half of that value. So the graph of 2 to the x looks like this. It starts out really close to the x-axis and then shoots up very quickly after x equals 0. So then it starts to go up very steep and shoots up quite dramatically. What is the domain, range, and so on? So for 2 to the x, the domain is any real number. So I can plug in any real number I'd like in for x. Positive, negative, it doesn't matter. The range, however, what I can get out is only positive. So you'll notice that I don't have any part of the graph below the x-axis. There are no zeros of this function. The range is every positive real number. So maybe I should put zeros. None. This function is always increasing. So it's increasing on its entire range, and it's decreasing never. And there are no local maximums, there are no local minimums. Let's plot, why don't we plot 3 to the x on the same axis to see the behavior of that graph. What happens if I change the 2 to a 3? So if I graphed 3 to the x, if I plug in 1, I'd be up here at 3. And if I plugged in 2, I'd be way up here at 9, which is off my screen. This graph still crosses the axis at this value because anything to the 0 power is 1. So the graph still goes through this value. If I plug in negative 1, I get 1/3, so I'm down here. And plug in negative 2, I get 1/9, which is even closer to the x-axis. So this graph, 3 to the x, has even more extreme behavior. It's even closer to the x-axis, crosses through this same value here, but then shoots up even more rapidly and looks like this. That's the graph of 3 to the x. The graph of 10 to the x is starting to get absolutely ridiculous. The graph of 10 to the x, I'm not going to draw because it'll make my picture look messy, but the graph of 10 to the x would look almost like a 90-degree angle. Not quite. I mean, it would have some curve in it, but it would go almost flat against the x-axis, cross through this point, and shoot almost straight up. I mean, it's still going to the right, but I mean, its behavior is extreme. Maybe I should plot in red, finally, the graph of 1/2 to the x power. So the graph of 1/2 to the x power, let's plug in some points. This, if you'll notice, is actually equal to 1/2 to the x power. It's going to be similar to the graph of 2 to the x, but I'm just going to reflect about the axis. Maybe you could see that more carefully if I write this as 2 to the negative x power. So the graph of 2 to the x and 2 to the negative x are the same, except you replace an x with a negative x. That reflects about the y-axis. So the graph will look like this. It'll be the same as 2 to the x, but flipped over. So let's see if I could draw that nicely. So I have a point here. I have a point here. Crosses through that same value. Goes half, half, half. So let me try to sketch a red curve that passes through those lines. So that's a good approximation of what the graph looks like. Now, what will be difficult for anybody to understand, I'm not even sure the human brain can comprehend it, is how fast exponential growth is. So these functions grow exceedingly fast. Again, it's growing so fast, it really is difficult to comprehend. For example, if I take this function 2 to the x and I go over to 2 to the 300, so if I go 300 units over this way, I mean, that wouldn't be that far to draw. Maybe I could actually draw 300. It'd take a long piece of paper, but I could do it, you know. However, 2 to the 300 is so extremely large, this is more than the number of atoms in the known universe. That's just 2 to the 300. What about 2 to the 400 or 2 to the 405? This is so absolutely insanely large. The human brain really has difficult wrapping its mind around it. So what about 3 to the 500 power? It's insane. Let's finish this video by drawing a graph of a related function to an exponential function. So we've seen earlier in this course that we can shift graphs around and draw variations on a curve that we already understand. So how about if I graphed negative 2 to the x plus 1 power minus 3. So here's what I'm doing. I'm taking the graph of 2 to the x and I'm shifting it to the left by 1. So if I take the graph of 2 to the x and I shift it to the left by 1, I will get the graph of 2 to the x plus 1 power. Then I could shift it down by 3. So if I shift down by 3, that accounts for this minus 1. So now I'll have 2 to the x plus 1 minus 3. And then I'm going to multiply the whole thing by a negative. That means I'm going to reflect about the x-axis. And that will give me the function I'm trying to draw. So I believe if you do all this, so I'm going to shift it left, I'm going to shift it down by 3. So if I shift everything down by 3, the new x-axis is going to be down at -3. And then if I reflect about the x-axis, I'm going to get almost like an asymptote at x equals 3. And I believe if you do these operations, you'll get a picture that looks something like this. Let's write down the domain and range of this function. So the domain is all real numbers. You can plug in any real number you'd like into an exponential function, but you can't get out any number you'd like. In this example, the range is -infinity up to 3, and this function is always decreasing. Okay, great.